What do rockets blasting off, runners sprinting, and hockey pucks gliding on ice all have in common? They all follow three simple rules of motion. Let's start with the first law. Newton's first law states that an object at rest will stay at rest, and an object in motion will stay in motion unless acted upon by an unbalanced force. But what does this mean? Let's find out. Newton's first law is also known as the law of inertia. When we use the word inertia, we're talking about a tendency of an object to resist a change in motion. So this is why we wear seatbelts. When a car suddenly stops, our bodies tend to continue moving forward, and the seatbelt restrains us, keeps us from hitting the dashboard or the steering wheel. In air hockey, once the air hockey puck is moving, its tendency is to keep moving until it hits something like the wall of the air hockey table. Let's take a closer look at what we mean when we say an object in motion will stay in motion. By that, what we're saying is that the object will continue at a constant velocity. And when we say constant velocity, we're saying constant speed in a straight line, because velocity is speed and direction. And what do we mean by an unbalanced force? Sometimes we refer to this unbalanced force as a net force. So if the forces are unbalanced, we say that there is a net force on the object. When we say that the forces are balanced, what we mean is that all the forces cancel out. When all the forces cancel out, the object's motion stays the same, which means if it's at rest, it'll stay at rest. If it's moving, it'll continue at constant velocity. Let's take a look at some examples where the forces are balanced. So here we have an object. There's a force to the right and a force to the left, and they're balanced. They're equal in an opposite direction, so we can say that the forces acting on this object are balanced. Here we have a second object with four forces. The force to the left cancels out the force to the right, the force up cancels out the force going down, and so once again we can say the forces acting on this object are balanced. Sometimes the forces might not be directly in opposite direction, but maybe they have components that are balancing the forces. So this force at an angle has a component to the right, and this component balances this force, and this component right here balances this force. So once again, we can say that the forces on this object are balanced. When these forces are balanced, we sometimes write this in symbol form, so the net force equals 0. And we need to remember that whenever it's at rest and the forces are balanced, it will stay at rest. If it's in motion and the forces are balanced, they will continue at constant velocity. Whenever the forces are balanced or there are no forces, we can know that the acceleration will be 0. This means that an object might be at rest and stay at rest, or it might have a non-zero velocity, which means that it is moving. And if it's moving, it'll continue moving at constant velocity. Now, a couple things students often forget are this, that objects can move without a force. They think that you must have a net force in order for an object to move, but there does not have to be a force. If an object's already moving, it'll continue moving. And also, students often forget that force is only needed to change motion. So when we say change motion, we're saying to speed it up, or slowing down, or change direction. So remember once again that if an object is at rest and the forces are balanced, it'll stay at rest, or if there's no forces, it'll stay at rest. If it's in motion and the forces are balanced or there's no force, they'll continue at constant velocity. Now, what happens when the forces are unbalanced? When we say that the forces are unbalanced, what we're saying is the forces do not cancel out. And when that happens, then the object's motion will change. Sometimes we'll write this as net force is not equal to 0. And let's take a look at some examples here. In this first diagram, we have a force to the right and nothing to the left. And so nothing's balancing this force. So the forces on this object, we would say, are unbalanced and has a net force. The second object does have two forces in opposite direction, but notice that this one is longer than the other force, and so they don't cancel out. So the forces on this object is also unbalanced. This object has a force pulling it at an angle, and there's nothing on the opposite side to cancel either the force itself or the components of the force. So we'd say that the forces on this object is also unbalanced. Whenever the forces are unbalanced, then we know that there is an acceleration. That means the object's speed will either be speeding up, or the object will be slowing down, or the object will be changing direction. All right, let's take a look at a concept check question. True or false? Motion requires a continuous force. The answer is false because once an object is in motion, its tendency is to stay in motion, and a force is only needed in order to change its state of motion, which means to speed it up, slowing down, or change direction. But if it's just moving at constant speed in a straight line, then no force is needed. Here's another concept check question. If forces on an object are unbalanced, what will happen to its motion? There are three possibilities. Number one, it could speed up. Number two, it could slow down. Number three, it could change direction, or it could be a combination of these. So the big idea is that a force is not needed to keep an object moving, but that if there is a net force on an object, then it will change its state of motion. Now let's take a look at Newton's second law, which states that the acceleration is equal to the net force divided by the mass. So the net force, the net part, is telling us the sum of the forces, and it's important to consider the direction of the forces. So we're considering all the forces acting on the object and taking into account their direction and dividing that by the mass, and that gives you the acceleration. The unit for acceleration is meters per second squared, the unit for force is newtons, and the unit for mass is kilograms. So imagine you have a shopping cart here, and here's the force to the right, and it's got a certain amount of mass. And as a result of the force, it has an acceleration. So the greater the force, the greater the acceleration. Now, the mass has an inverse relationship to the acceleration. So if you have a greater mass, keeping force the same, the acceleration will decrease. And remember that the acceleration is in the same direction as the net force. So if the net force is to the right, the acceleration will be to the right. The net force to the left, the acceleration will be to the left. When thinking about Newton's second law, it's helpful to think about how the net force affects the acceleration and how the mass affects the acceleration. The acceleration is directly proportional to the net force, and what that means is that if you were to double the net force, you would double the acceleration. If you triple the net force, you would triple the acceleration. If you cut the force in half, you would cut the acceleration in half as well. And the acceleration is inversely proportional to the mass. And what that means is that if you were to double the mass, you would cut the acceleration in half. If you triple the mass, you would cut the acceleration by a third. And if you were to cut the mass by a half, you would double the acceleration. So the acceleration and force change in the same way. You increase the force, you increase the acceleration. The acceleration and mass changes in opposite ways. If you increase the mass, you decrease the acceleration. Let's take a look at a calculation problem for Newton's second law. A 5 kilogram box is being pushed to the right with a force of 20 newtons, while friction pushes to the left with a force of 8 newtons. What is the acceleration of the box? So we always want to start with a force diagram, and you'll notice that the normal force and the gravity force here are balanced, so those are not going to cause an acceleration, but the applied force to the right is greater than the friction force, the kinetic friction force to the left. And we're going to indicate our positive direction, right as positive, and we're going to use our Newton's second law equation, A equals net force divided by the mass. The net force is all the force going in the positive direction minus all the force going in the negative direction, and we're going to take that divided by the mass, and we're going to do our substitution. So 20 newtons minus 8 newtons divided by 5 kilograms. And the acceleration that we get is 2.4 meters per second squared. One of my biggest tips for these type of problem is to draw a force diagram. And then after that, making sure that you show all your work. So including the equation, doing your substitution, and then solving for the answer. Now let's take a look at Newton's third law, which states that for every action force, there's an equal and opposite reaction force. But what does that actually mean? First, this law is telling us that all forces are an interaction between two objects. So it doesn't matter what force we're talking about, whether it's gravity force or normal force or tension force, all forces are an interaction between two objects. So here you can see the boy pushing the wall to the right. So this is an interaction between the boy and the wall. And notice that this results in two forces, the boy pushing the wall to the right and the wall pushing the boy to the left. Now, I'm using what's called the agent-victim notation here, and what this means is that it's saying that the force of the hand pushing on the wall, and this notation here, this representation here is saying that the force of the wall on the hand. This agent-victim notation reminds us that these two forces right here are action-reaction forces. All forces come in pairs. So an easy way to think about the two forces is to use this template. A pushes B, B pushes A, or A pulls B, B pulls A. So here we have a runner running to the right. So his foot or shoe is pushing the ground to the left. And as he pushes to the left, the ground pushes the runner to the right. So let's take a look over here. Here we have a shoe, or think of this as the person is running, pushing off with their foot. So the foot is pushing the ground to the left, and the ground is pushing the foot to the right. And here's our notation, our agent-victim notation, which states that the force of the ground is pushing the foot to the right, and the force of the foot is pushing the ground to the left. And so these two forces are our action-reaction pairs. Since action-reaction forces are equal in opposite direction, do they balance out? The answer is no. And let's take a look at why not. So action-reaction forces act on different objects. So here is a shoe kicking the soccer ball to the right. The reaction force is the soccer ball pushing the shoe to the left. So you might say, okay, aren't these forces balancing each other out? And the answer is that they do not balance each other out because they act on different objects. So this is key right here. Different objects. If the forces were on the same object, like in this situation, the force to the right, the force to the left, then the forces would be balanced. But that is not the case. When we're talking about Newton's third law, the action forces are on different objects. So this force is on the soccer ball, and this force is on the shoe. Action-reaction forces are equal, like we stated earlier, and it doesn't matter if the object is moving or has a different size. So let's take a look at an example. Here we have a large truck right here, and we have a little car. And so you might think, how could the forces be the same? Isn't the large truck exerting a greater force on the little car? Because it seems that the effect on the little car is going to be greater than on the big truck. So here we need to distinguish between a force and its effect on the object. So although the action and reaction forces are equal, the acceleration or the effect on the objects may be different. Remember that acceleration is equal to the net force divided by the mass. So the forces can be the same, but the acceleration is different because they have different masses. The truck has a large mass and the little car has a small mass. And so even though they have the same force acting on them, the acceleration is different. So here's another example where the action-reaction forces are equal, but the acceleration or the effect on the objects is different. So here we have the earth pulling on the tennis ball, and the tennis ball is pulling on the earth up. But we don't really notice that because when we look at the earth, we don't really see it move when we drop a tennis ball. But when we look at the tennis ball, it definitely is falling, and we can see it accelerate. So how come we don't see the earth accelerate upward? So the answer has to do with the fact that acceleration is different than a force. So even though they have an equal and opposite force, their acceleration is different because they have a different mass. The Earth has a way bigger mass, and this big M represents the mass of the Earth. And the tennis ball has a small mass, and this little M represents the mass of the tennis ball. And the effect or the acceleration isn't just dependent on the force, it's also dependent on the mass. And the Earth has a way bigger mass than the tennis ball here. And so as a result, we have a bigger denominator here. And so our number here, our acceleration, is going to be very, very small. And over here on the left-hand side, we have a really small denominator. And so our acceleration is going to be very, very big. So we will notice the tennis ball falling. We'll notice the effect of the force acting on the tennis ball. We can see that in its acceleration. But the Earth, because it's so much more massive, the acceleration is so small that we hardly even notice that. Now let's take a look at the classic horse and cart problem. If the horse pulls on the cart and the cart pulls on the horse the same amount of force, how can the horse and the cart ever move? So we talked about how action-reaction forces are equal and in opposite direction. So how can the horse ever pull this cart forward? To answer this question, we need to remember that the action-reaction forces act on different objects. They do not cancel out. And that motion depends on the net external force on the system. So if this horse is actually able to go forward, that means there is a net external force on the horse, which means that there are other forces involved. So the first part of the answer to this problem is to know that the action-reaction forces are not the only forces here. There are other forces. Well, what are the other forces? Well, the horse is pushing the ground back, and the ground is pushing the horse forward. And you see that represented by the red arrow there and the red arrow there. So if we take a look at just the horse, there are two forces acting on the horse. There is the force of the ground pushing the horse to the right, and then there's the force of the cart pulling the horse to the left. And as long as the force to the right, the red arrow here, is greater than the force to the left, the blue arrow here, then the horse will be able to accelerate and move towards the right. Here are a couple Newton's third law common misconceptions. The first is that heavier objects push harder, and the second is that moving objects exert a bigger force. But the truth is that action-reaction forces pairs are always equal, okay, in magnitude, and this is regardless of the mass. It doesn't matter if one object is heavier or lighter, and it doesn't matter if it's moving or not moving. The action-reaction forces are always equal in opposite direction. If you found this video helpful, check out my next video where I show you how to solve 6 classic dynamic problems.